Hey guys, welcome back to Recreational Sniper. Tonight we're going to go over the horizontal Coriolis effect, okay? Or the horizontal Coriolis force. Basically, it's an apparent force. It's just kind of a force of relativity. So here I have our Earth, and obviously it's not green and blue and all that stuff, but this is more for demonstrational purposes. We have a foam ball with some lines on it. So this is going to be your equator line. This is going to be a latitude line just for reference, and another latitude line. We only need this one longitudinal line just for a reference point so that you know we are in line with our axis from the North Pole to the South Pole. And I got a little compass on here. Okay, so I'm just going to move that over there. All right, so here we go. When we're looking at horizontal Coriolis, in the northern hemisphere, your horizontal Coriolis deflection is always going to be to the right, and that's independent of whatever direction you're shooting. It doesn't matter. It's always going to be the right, and in the southern hemisphere, it's going to be to the left, and that has to do with because we are not on a flat plane. Our planet is a sphere, basically a big ball, and because of the shape of that, our deflection on the northern hemisphere is always going to be to the right, and on the southern hemisphere it's always going to be left. So we're gonna get out our pretend stuff here, and we are going to hopefully not twist your brain a little too much. So here we go. Our Earth spins upon its axis this direction, right? We got north, south, east, west, right? But our Earth spins counterclockwise rotation, and it spins on its axis kind of like this. Something like that. And this is the reason why the sun rises in the east, because the sun's out here, is because we're rotating towards it from the west to the east. Okay? So if we take our compass and we're sitting exactly on the equator and we're pointing north, south, east, and west, and we decide that we want to go exactly west, or we're going to shoot a gun west, right? So if we do that, it's going to follow the equator all the way around, right? Now, what happens if we're up higher towards the north on a different latitude? What happens then? Okay, so you would think that, you know, if we shoot to the west, if we're shooting due west, that we would just follow that latitude, right? Well, we're on a sphere, so you got to keep that in mind. If we were on a flat plane, you know, like those flat earth guys, if we were following their rules and theories, it would just, the bullet would travel, if we shot that direction perfect, you know, with perfectly to the west on our latitude, it would keep following that latitude all the way around until it reached back, right? I mean, theoretically, well, let's just pretend that a bullet will circumnavigate the globe. But we're not on a flat plane. Our Earth is curved. So what happens when we shoot west? So check this out. When we shoot west, you see the blue line? Now, all of a sudden, we're kind of making this, but that way is it's going to make a ring going to the west, and you are shooting west, right? But why does it dip below the equator? And at the opposite side of the planet, it's the same space. You're back on the opposite, pretty much you are on the opposite latitude there. And then it comes back around, kind of arcs, you know, back to there. But this is, if you spin it this way, it's a straight line. I'm not doing that very good, but this is a straight line all the way around, right? So because that's the trajectory of our round, but because that we are on a different latitude, we're not at the equator, we're up one, our direction is going to travel differently. So now when it comes to the horizontal Coriolis effect, there's a little bit of another part that's going to kind of come into play, and this is actually what is happening to your bullet and why it's deflecting to the right, or appearing to deflect to the right. So say we shoot due west on our, say our latitude is that, which is the latitude of my home gun range that I like to use. Say we shoot that way, okay? Well, now a little bit of some external ballistics come into factor. So once the bullet leaves the barrel, leaves the muzzle, it is no longer attached to the surface of the earth, right? You as the shooter are attached to the ground. The gun's attached to you, and so you're moving with the earth, right? So keep that in mind. You're not going anywhere. You're moving with the earth. But when you launch the bullet into free flight, now it's not connected to the earth anymore. It's in the atmosphere. It's not grounded. So basically the earth can spin freely underneath it without actually affecting the trajectory of that bullet. So if you're shooting due west, right, at this target over here, because that's where it crosses, say we can shoot that far, and where it crosses the equator, that's where our target's at. So we're shooting due west at this target on the equator, right? Well, as that bullet's in flight and it's making its way over there, it's going to take time to get over there. And while it's taking its time to get there, it's sweet, slow time, the earth is also rotating this direction, right? It's going towards the bullet. So it's rotating this way. And so as the bullet is going that direction, what is happening? Your target is still moving on this longitudinal line, okay? So your bullet, even though you're kind of shooting that direction, your bullet is going to appear to veer to the right. And that's horizontal Coriolis. That's that apparent force, even though you're actually shooting straight. Hopefully that makes sense. The bullet's not actually turning to the right. Basically, it's your target is on a slightly different latitude than you are, and it's coming towards you. Or, well, it's not actually coming towards you, it's coming with you. And the bullet is in flight and it's not connected to the ground. So as it's moving toward it, the earth is slipping underneath that bullet, and your target is going with the earth, and it's on a slightly different latitude. So it moves apparently to the left, but that causes your apparent bullet impact to hit right. So hopefully that was not too much. Now, how do we fix that problem? How do we correct for that? That's, it's been done quite a bit. There's a lot of different equations that get relatively the same answer. Some people can argue that one equation works better than another. For me personally, this is one of those equations you're gonna have to work out in the field, and where I shoot at a bunch, there is no internet access out there, so I have to go out, take readings and stuff, and get like an average reading of barometric pressure, and so what I'm doing is not going to be exact. It's going to be as close as I can get. It's going to get me in the ballpark of being able to hit that target out there. So I kind of worked this out in advance, but we're going to get into this. The equation that I like to use, because it's simple and it's easy to run the calculator, you're less likely to make a mistake somewhere putting the wrong value in. But you're going to need to know what the omega constant is. You're going to need to know the range to your target in feet. You're going to need to know the time of flight. you're going to need to have a scientific calculator that can do trig functions so that you can take the sine of the latitude, and this should get you your deflection in feet. I may be wrong on that, but it seems like when I work it out that it's pretty dang close to what it should be. So your omega constant. The omega constant basically is just it's a numerical value assigned to the rotational speed of the Earth. That omega constant is 0.0000729, and that is just a value that you're always going to have to know. If you're doing any Coriolis effect calculation, you're going to have to know that value, so just keep that in mind. And then say we're shooting 1,000 yards, which is what I worked this equation out for. It kind of just made things easier to do it that way, so we don't have to get too complicated in converting all this stuff down here. So we're shooting 1,000 yards. 1,000 yards in feet is 3,000 feet. And your time of flight, this here is kind of tricky, and it's really important that you get it right for this to work. And for that to work, you're going to have to use a ballistic solver, ballistic calculator, because you're going to need to know the exact barometric pressure where you are at. You're going to need to know temperature where you're at and your ammunition temperature, and you're going to need to know what your muzzle velocity is. So I've worked this out in like a theoretical thing for a 1,000-yard shot using my rifle with a 185 grain Berger Juggernaut. So I got a time of flight to my target of 1.757 seconds. And then the latitude we are shooting on or from is 34.562537. And we take the sine of that. Anyways, we run this calculation and we get 0.281 feet. And we're going to multiply that by 12 to get the inches, and it's 2.62 inches. And then if you're looking at 1,000 yards, it's pretty easy to convert mils and minutes of angle. And this is the reason why I chose to go with 1,000 yards, is because it's just units of 10. And you can do this part in your head, but at 100 yards, 1 mil is 3.6 inches, right? So at 1,000 yards, 10 times that far, you just move the decimal, so it's 36 inches. So you divide 2.62 inches by 36, and it's going to give you 0.07 mils, roughly. Most mil radian scopes are going to be in 1/10 mil or 0.1 mil adjustments. So with a 0.07, you can probably go ahead and make one click on your scope. If you want to convert it to minutes of angle, you take 2.2 or 2.62, and you're going to divide that by 10.47. 10.47 being 10 times 1 minute of angle at 100 yards, which would be 1.047 inches. And you're going to get, go ahead and do that out, and you're going to get a 1/4 minute of angle. So one click on a 1/4 minute of angle scope. So yeah, that's pretty much it. And like I said, this whole thing, like knowing how to do this, really doesn't come into play until you're shooting 1,000 yards plus. Like, see here, it's on a mil radian scope. It's barely, like, you can round it up to one click, but really, I mean, you could either go one click or not go one click. It's such a small adjustment. Even at 1,000 yards, we're talking a little over 2.5 inches of deflection to the right on this latitude. Now, on a different latitude, that's going to change a little. If we're shooting a different bullet and we have a different flight speed, it's going to change a little. If we're shooting a different range, it's going to change a little. So what I'm just trying to say is 1,000 yards is probably the minimum that you're actually going to have to adjust for this. It's it's right at one minute of angle for that particular bullet. And like I said, that particular flight time, particular atmospheric conditions and whatnot, it's one click on the scope. You could argue that shooter error at that range, at 1,000 yards, is going to throw you off by one click, from round to round. So unless you're shooting groups that are smaller than 2.5 inches at 1,000 yards, which is extremely impressive. It has been done, but not very often. So there you go. That's horizontal Coriolis in a nutshell. Hopefully I didn't fry your brains too much with that. And then in the next video, we'll get into vertical Coriolis. I may do that one tomorrow, but hope you guys enjoyed this. If you got any questions or comments, leave those down below. And if you would, go ahead and hit that subscribe button and hit the like button. And we'll see you next time in the next video. Thank you for watching.